So in this video, we're going to be discussing Lab 10, the empirical formula of a hydrate. So we had looked at what a hydrate was in the previous lab, Lab 9, and we talked about how the hydrate is a compound that has water molecules loosely attached inside its crystal structure. And then when you heat the hydrate, what you will find is that that water of hydration will then leave that crystal structure. It'll excuse me, vaporize and come out and leave the compound which is called as an anhydrate, which is the substance without that water of hydration. Okay. So a hydrate is an inorganic compound that has a very specific number of loosely attached water molecules inside its crystal structure. So this water is referred to as the water of crystallization, or sometimes water of hydration. So when the hydrate is heated, those water molecules inside the crystal structure will then get separated, and the water vaporizes, leaving behind the ionic compound without the water of crystallization. So this compound without the water is called as the anhydrate. So if you take a hydrate, and this is the symbol for heat, you heat it, you get anhydrate. So this lab is about heating the hydrate of copper 2 sulfate and then trying to determine how many molecules of water is associated with one molecule of the copper 2 sulfate. All right. So you're basically trying to determine what the ratio of the water of crystallization is compared to one molecule, or more precisely 1 mole of the copper 2 sulfate. So in the second part of this lab, you will heat yet another hydrate. This is magnesium chloride, and again you will try to determine what the ratio of water molecules is with 1 molecule of, or rather 1 mole of the magnesium chloride. So you have copper 2 sulfate and hydrate in a solid blue crystals. You heat it and you get a white powder, the copper 2 sulfate, and then X is in the formula represents the unknown number of water molecules that has to be determined from this experiment and also by calculation from your data. So again, magnesium chloride hydrate, you heat it up and you get the magnesium chloride, the anhydrate, and then the water comes out. Now here, I think both of the compound and the anhydrate are white. This has got a white crystal structure. This has got a more finer white powdery kind of structure. So here it's not as visually clear as in the case of the copper 2 sulfate. So we talked about this, and I'd shown you some previous pictures where you're taking this blue stuff, which is the copper 2 sulfate hydrate, and then you heat it up and then you get the white powder, and that's the anhydrate without the water. And I had also shown you some pictures previously in the other lab where you're looking at the water of crystallization, those 5 water molecules strongly attracted to the positive copper. All right, so these are like bonds, kind of like physical bonds due to the attraction between opposite charges. Now this is not as strong as an ionic bond, so therefore it's easy to break it up with heat and get the water out of the compound. All right. So again, there's a network of that everywhere, and that's kind of in a way holding up that crystal structure and giving it that nice crystalline shape to the compound. So you take a crucible, add 5 grams of the copper 2 sulfate hydrate, and then record the mass. So the empty crucible is 88. So once you add 5 grams of the hydrate, the mass should be 93 grams. Place this now on a Bunsen burner, heat it for 2 minutes till all the vapors stop forming. That means you've driven out all the water. Now this indicates that all of that water of crystallization has been released from the hydrate. Cool the crucible on the workbench and then mass it again. All right, so now the crucible just has the anhydrate, so it's going to weigh less than what it weighed previously before the heating step. So in the second experiment, again, you're taking your crucible, adding 5 grams of, this time, the magnesium chloride hydrate. And so that, again, the empty crucible is 88. Once you add 5 grams to it, it goes up to 93. Now place this also on a Bunsen burner for 2 minutes and heat it till the vapors stop forming. And then cool this crucible and then mass it again. All right, so this time the crucible is after the heating step is going to weigh less. So what are the equations before knowing how much water is associated with the copper 2 sulfate in the hydrate? So you would write it in this form, all right, putting an X to indicate that you don't know what this number is. Okay, and then you would indicate the reaction in this manner, showing the arrow with the triangle for heat, and then on the copper 2 sulfate on the product side, and X H2O on the product side. Okay. So the mass of the crucible and hydrate is 93. 88 plus that 5 is 93. Now that mass went down after the heating step because you've driven out all the water, and so it went down to 91.196. Okay. So if you subtract this number, the 91.196 from 93, you get the mass of the water that left the hydrate sample or was present in the hydrate sample before the heating. So this is the mass of the water that was present in the hydrate. You take that mass, 1.804, and divide it by 18. Why 18? Because this is the molar mass of water, is 18 grams per mole. And then you get 0.10 mole. All right, so this is the mole of H2O. Now, initially you took 5 grams of the hydrate. All right, so if you subtract the mass of water from the hydrate, you get the mass of the anhydrate, which is the copper 2 sulfate. Okay, so that's 3.196 grams. So you take that number, the 3.196, and divide it by 159. Why 159? 159 is the molar mass of copper 2 sulfate, right? So you get 0.020 mole of the anhydrate, which is the copper 2 sulfate, right? So then you will look at these two numbers for the moles, which is the lower number. This is 0.020. So if you divide 0.020 by 0.020, you get 1. If you divide 0.1 by 0.020, you get 5, right? So that means this is water, remember, there's 5 moles of water for every mole of the copper 2 sulfate. All right, so therefore the empirical formula of the hydrate for copper 2 sulfate is CuSO4 dot 5H2O. Okay, you have to put the dot in there in the formula. This indicates that this water is not part of the molecular formula of the compound. It's kind of separate because it's the water of crystallization. And then the decomposition of magnesium chloride hydrate. Again, you would represent that decomposition reaction in this manner because you don't know how many waters are associated with the magnesium chloride. Okay, so this is how you would write the equation for the decomposition. Again, the mass of the crucible is 88. Then once you add 5 grams of the magnesium chloride hydrate, it goes up to 93. Okay, so 93, and then once you heat it, all of the water is driven out and you get the crucible plus anhydrate. So if you subtract the 92.148 minus the 93, you get 0.852 grams. That's the mass of the water that was driven out of the sample or was present in the sample before the heating step. So you take the mass of water, 0.852, divide it by the molar mass of water, and you get 0.047 mole of water. So the mass of the hydrate was 5 grams. You subtract the mass of water from it and you get 4.148 grams, which is the grams of magnesium chloride anhydrate. Okay, magnesium chloride is molar mass is 95.211. So you divide 4.148 by 95.211 and you get 0.044 mole for magnesium chloride. Okay, now 0.044 and 0.047 are very similar. So if you divide both this by 0.044, you get 1. And if you divide 0.047 by 0.044, you get 1. All right. So the empirical formula of the hydrate for magnesium chloride is MgCl2.H2O. They are in a 1:1 ratio. So the aim of both experiments is to find the number of water molecules associated with each molecule, or rather, to be more precise, each mole of the pure anhydrate salt. So I predicted that in experiment 1, the number of water molecules present in the copper 2 sulfate hydrate would be around 5. This was because I had a previous knowledge about this compound. In experiment 2, I didn't have as much experience with the magnesium chloride hydrate, and so I didn't know how many molecules of water would be associated with this compound. Procedure, we went through that in the previous slide. Observations. So when you heat the blue copper 2 sulfate hydrate crystals, they slowly lose their water of crystallization and form that white powdery anhydrous copper 2 sulfate. Magnesium chloride hydrate, when heated, it released its water, forming again the pure anhydrate salt. Now there's not much of a color change here because both of them are white, except that one has a more crystal looking structure and the other one kind of looks like a white powder. Alright, we'll stop here and continue this in the next video.